In Module 6, we're going to talk a little bit about additional libraries that are included as part of the C standard. Now, we've talked a little bit earlier about how to create our own libraries, and we've used a number of different capabilities that are provided in things like the C standard library and the standard I/O library. We're going to go into a lot more detail on just a selection of these. I'm going to give a very brief overview of some of the commonly used C libraries and what kind of functions they contain. And then we're going to do a deeper dive into three of these libraries, which are the string library, the math library, and the standard I/O library that we've touched on earlier. So there are a lot of libraries that come packaged with the C compiler. And this means that there is a lot of functionality available for you to use whenever you're writing programs that these libraries are appropriate for. Many of these libraries are useful for providing functionality for applications, which means these are things that are useful in user space above any kind of significant operating system abstraction layer. Many of these are not necessarily available when you're writing system services within the operating system itself. That's a problem for a different day when you actually start writing that kind of code. For now, it's really useful to know about all of this functionality that you can use when you're writing C code. So we have touched very briefly on the standard I/O library. We use the printf and the print char and the put s, or the put char and put s functions. This one does go significantly deeper. It supports a lot of more generic file I/O, file input-output. There are quite a few libraries for performing operations on specific data types. There's the C-type library which provides functionality for operating on character data, things like converting between character and integer, doing other kinds of encoding, decoding operations. The string library is one that we're going to go into in more detail. It talks about how to do a variety of different operations on arrays, on strings, on sequential blocks of memory. We talked a bit about the C standard library. We used things like malloc and free and exit and null that were all provided in the C standard library. There is a whole lot there that you can go into a lot more detail on. There is a math library for performing a variety of mathematical functions. We're going to dive into this one a little bit. There's a library called signal.h, which provides ability to handle system level signals. These are things like how your program can respond if a user tries to terminate the program, or if the system tries to terminate the program, your program can actually catch that signal and gracefully close down the program, save whatever files are open, save any state you need to save. It's very useful things to be able to do. There are two different libraries for doing date and time functionality, time.h and sys/time.h. One of these does simple time operations and one does system timekeeping. That's high level difference. And then there are a variety of other libraries for working with constants and data types and ranges. For example, the limits library gives you things like the maximum 32-bit signed integer, minimum 32-bit signed integer constants that are sometimes nice to have. And so there's an entire library of those constants that you can use in your programs by simply including this library. And there are a lot of other libraries. There are easily dozens of libraries included with a typical C compiler. GCC includes dozens of them on its own, in addition to things for other languages. So in this first module, as submodule, as part of Module 6, we're going to do a little bit of a dive into the string library. We're not going to cover everything in the string library, but I just want to highlight some of the main functionality that's included, that are function implementations that are available for you to use. So the string.h library includes a collection of functions that operate on char star and void star variables. Now, char star we know those are strings. Void star we've talked about as being generic memory addresses. So this means that the string library doesn't just perform string operations, it also performs some generic memory manipulation operations, which is nice. This is good functionality to have, but the name is just a little bit misleading, and sometimes you have to remember that these memory operations are in the string library and not somewhere else like a memory library or the C standard library. So a lot of these functions that are included in the string library are relatively simple functions. These are things that you could easily write on your own. Some of them are just a few lines of code. But the benefit of having these libraries is that the library code is very, very heavily optimized. So these are like the best possible way to implement these functions. And so they're going to be very clean and very fast. So you can implement them on your own, but the implementations that are in the standard libraries, which most of which are open source, are very fast, and there's typically no reason not to use most of them. So we're going to go into some details on some of the useful functions within the string library. The first one that is very commonly used is the string length function. Now the string length function takes a character array, operates on a character array, and simply steps through until it finds a null character. So we talked about this earlier, where C assumes every string is null terminated, and eventually there will be a null character somewhere within either the static array or a malloc amount of space, a char star. And so this will simply iterate through until it finds the first null character and return the number of characters that it stepped past before finding that null character. Now this returns a data type that is called a size underscore t, and size underscore t is nothing other than an alias for an unsigned long. And rather than writing unsigned long millions of times, they created a custom data type, which means if you're using the string library, this is the data type that you can also use. This is also the return type of things like the size of function, which we talked about earlier as having a return type of unsigned long. So this is nothing other than an unsigned integer, which a string length must necessarily be. We can also do more active operations in the string library. We can do things like append one string onto the end of another. There are two functions built into the string.h library that perform string concatenation or string appending. The first one takes two character arrays as arguments. The first is the destination array, and the second is the source array. And stringcat simply starts at the first null character in the destination array and starts to copy all of the characters in the source array up until the first null character, and including that null character from the source array, which means that the original null character in the destination is removed. It's overwritten by the first character in the source, and the null termination character in the source is also copied so that the new the destination string now has a valid null character at the end. Now this function is known to be a little bit dangerous because, say for example, my destination string was malloced to store 100 bytes. My source string was malloced to store 500 bytes. I can call this function and it will happily continue to write past the 100 bytes that I've malloced in my destination. So even if my destination's space is not large enough, stringcat will happily write well past the end of that array to concatenate one string onto the other. So this is not a safe function. This is not a safe implementation. It can cause buffer overflows and problems like buffer overflows. The second implementation of the string append, the string ncat is similar, except you have a maximum number of characters that you are allowed to copy from the source array into the destination array. And supposedly when someone calls this function, they provide the maximum number of characters according to the amount of space that's available in the destination array without overwriting past the end of that array. So this is a little bit safer, potentially, if you use it correctly. It's not guaranteed to be safe. I can have a destination array of length 100. I can give it a value of n significantly larger than that, and it will happily do what I asked it to do. But there is just a little bit more control, so you can try to use it safely. One interesting note about the stringcat functions, if the destination is originally empty, stringcat makes a copy of the source. So this is also does double duty as a string copy function when you have an empty destination. Now there's a generic function built in that instead of operating on strings operates on memory, and this function is called memset, and this is simply a way to fill a region of memory with a repeated value. This is commonly used for clearing memory. You can set a whole range of memory to the value 0. This is a really nice thing that's useful in a lot of programs. The way that memset works is you give it a region. You simply give it a pointer where you want it to start. You give it a value. It actually takes an integer value, but it will convert that integer value into a 1 byte integer, simply a byte value. And then you give it the number of bytes that you want it to fill starting from that starting position S. So the easy way that this is commonly used, suppose I have some sort of a data structure, building on our previous example, suppose I want to empty out one of the cars in my garage. I can go into that particular entry in the garage and just say, hey, fill that entire entry with zeros. Here's how many zeros to fill. We know the size of each car because we can use the size of function. We want to set every byte to 0, and this is a valid thing to do. Memset actually does return a pointer. I believe it just returns a pointer either to the beginning or the end of the region. I don't exactly remember. If you don't want to catch that return value, you don't have to, which is shown in this example here. I simply call memset and I let the return value disappear. This is a legal thing to do. We can do copy operations, string copy and mem copy, meaning we can copy character strings. We can also copy arbitrary regions of memory. So string copy operates, basically we give it a source and a destination. Again, this copies anything from our source string into our destination string. This is similar to string append if the destination is empty. Otherwise, this overwrites the contents of the destination array if there was anything previously there. And similarly, string n copy copies at most n values. It will copy fewer if the source is shorter than that number, but it will copy at most n values. One of the catches with this is if you tell it to copy n values and the source is longer than that, those n values may not include the null termination character, and this will not necessarily include one for you. The third example here is the memcopy operation. This does a similar thing, except it operates on raw byte by byte copying. So this doesn't need to be character data. It doesn't need to be strings. It won't have null terminations. This is arbitrary memory contents. You give it a memory location to start copying from, a memory location to copy to, and the number of bytes to copy. In this case, there's no variant that doesn't have the n parameter, because there's no way of knowing otherwise when you want someone to stop. Strings use the null termination character. With generic memory, there's no such thing. So here you must specify the number of bytes that you want to copy. This is very useful for moving data around within a system because this can operate independent of the data type, because you can just cast things to void star and memcopy will operate on the raw byte values. The string library also allows us to do things like string comparison. There are two different functions for trying to compare, for doing lexicographic comparison between strings. The way that string comp works is you give it two strings. They're marked as constants because the function is not allowed to change them. The string comp gets two strings. If the two strings are identical all the way up to the location and existence of their null termination character, string comp will return a 0. So in this case, equal means 0. A negative integer will be returned if the first string is lexicographically less than the second string, meaning it occurs first if they're sorted. Or will return a positive integer if S2 is less than S1, meaning S1 comes after S2. So the interpretation of the return value is very important here, and this is where it really helps to look up the documentation for the string comp function to make sure you're interpreting the comparison value correctly. String ncomp does a very similar comparison, except it's only based on the first n characters of the two strings, or up to the first n characters of the two strings, and it returns similar to the first one. Now, this is all I wanted to really go into in terms of the string library, because most of this I wanted to try and just give you an idea of what kind of functionality is provided within the string library. There is more than this. I didn't go through the entire library. There's more that can be done. I'm not going to give you examples of how to use all of these. You can find a lot of examples online. What I am going to do is I'm going to bring up the terminal and I'm going to go through one thing that we can do, building on our previous examples, to improve some of our code by using the functionality of the string library. And in this case, what I'm going to show is our existing car implementation. So earlier we had an implementation of the build function in car that simply pointed the struct members to the strings that were passed as arguments. And I said that this is okay if we're pretty sure that no one's ever going to change those existing strings. In reality, it might be nice when someone gives a string to a build function to make a local copy, because we're building a car, we're building a data structure. We probably want it to be completely self-contained. So the way that I'm going to modify the car data structure is I'm actually going to use the string copy operation to copy the contents of the strings provided into the build function into the actual car data structure. Now this is relatively straightforward to do, but it requires a little bit more use of malloc to create space for the copies of the strings so that we can copy into memory dynamically. So now the function prototype for the build function is the same. We're creating a pointer to a car. We're passing it strings for the make, model, year, and color of the car. We're initially mallocing space to hold the car object itself. If that car object is not null, we're going to continue on and malloc space for the make, model, and color strings that we're going to copy. In order to do that, we have to know how much space we need to allocate. So for the make, what we're going to do is we're going to allocate exactly the number of bytes that we need to store the make string. And in fact, what we should be doing here is we should add 1. And why should we add 1 is we need a space to store the null termination character. String length will not necessarily include the null termination character. So if we need to include all of the characters included in the string itself, as well as the null termination character, we can use the string length function in the string library to compute that length, then give that +1 to malloc and get exactly the amount of space that we need. for the make, model, and color strings. We can then do some additional error checking to make sure all of those mallocs were successful. We actually got the space that we need. In this case, if any of them fail, I'm just returning. We could separate those out if we wanted to. And then, of course, I'm using a string copy to copy from the existing string make, the one that was passed as an argument to the build function, into the local C make placeholder. So this is the space that we've malloced. We know there's enough space to store that because we malloced exactly that amount of space. String copy will include the null termination character, so that's why we need the +1 to be able to store the make, the model, the color. The year is just a number that's easy to work with, and we're done. So this improves the car by essentially making it safer. It makes our car builder safer by making a copy of the string that was passed rather than simply pointing to whatever the program provided. Because it's possible that a program calls build and then actually deallocates the strings that were used and passed to this function. And if that happens and we continue to use the result of our previous build, we might accidentally point to things that have been freed. So this is safer because it prevents a use after free issue. Here we are explicitly creating the strings and the placeholders for each car. And when we now unbuild or destroy a car, we then have to remember to go and free all of the space that was used for this car. But this is a safer use, and we can do this easily because we now have the string library functionality provided for us. Okay, so that was our example for the string library, and this is as far as I'm going to go into detail on the string library, which means this is the end of our module. The next module will go into some detail on the math library.